Hello and welcome to the breaker track. Today we are going to be listening to Katz, who will be presenting about JavaScript obfuscation. Katz is a principal lead security researcher with Akamai Technologies. As you'll notice to the right, you'll be able to submit any questions that you have for during the presentation, and we'll be taking those questions during the last 10 minutes of our session today. So please note that that chat function is disabled for you here in Zoom, but you can submit those questions in the Whova app. So at this time, I'd like to go ahead and give the mic over to and we'll go ahead and get going. Thank you for attending today.
Thank you, Christina. Let me just share my screen. Hi, everybody. So what I'm going to present to you today is a research about JavaScript obfuscation. It's all about the packer. Let's get started with a short introduction of myself. I'm a former OWASP Israel chapter lead, a thing that I'm really proud doing in the past and leading the activity on Israeli chapter. I'm a data-driven security researcher, and hopefully that will make sense toward the end of the presentation, as I will present a lot of data that is associated, research that is associated with data. When I try to define my role in life, in my professional life, I'm saying that I'm trying to move security challenge into the science and solution space. That's part of the thing that I'm doing, and hopefully that also will make sense for the end of the presentation. And I have, and that's the most important thing here today, I have a really boring social network persona. Therefore, I don't encourage any of you to follow me at _Katz at Twitter. Don't do that. Boring persona, don't do that. Again. Cool. So let's get started. So how did I end up here today? So over 18 months ago, I was doing some research about JavaScript obfuscation, and the outcome of that research was me publishing 3 different blog posts. The first blog post was more about a dictionary kind of blogs mentioning the different techniques being used for obfuscating JavaScript. The second blog was more into the trend and thing that we're seeing out there when it comes to obfuscation and phishing website. And we were able to see some trend in how many of those phishing websites are being obfuscated or those techniques being used on those phishing websites. And the third blog, which is related to the image that you see in front of you, was me taking a relatively simple obfuscated JavaScript file and breaking it down to small pieces, trying to explain what really happened on that file. And as you can see on this image, it's not an easy file to read. And while I was doing that kind of research, I asked myself the question, well, I can do that once, right? Or even a few times, but it's very time-consuming effort to do that. And it's not easy to do that in many cases. And I asked myself a question whether I would be able to detect those kind of malicious obfuscated JavaScript files in a much higher scale and create some sort of environment to do that. So that was the beginning of my research, and as part of that, I created I created 4 kind of objectives for me for that research, and here are those objectives. So the first objective was to try to figure out if I can find a technique that will enable me to detect an obfuscated JavaScript, but more preferably being able to detect a malicious JavaScript. The second objective, do that at scale, right? It's not about me doing that or others doing that kind of work. We knew that in a scale of hundreds or even 1,000 per day files being scanned and being able to detect those files. The third objective, which is actually will derive from the second one, is as I had some limitations, and my research was in the context of looking into traffic and making decisions based on the data being transferred over traffic over the wire, I needed to use a technique that is not technique that will enable me to render those JavaScript files. Meaning I need to look on a static kind of code analysis approach, look into the files being transferred, make decision based on that. And much of that is related to performance, right? Once you take a JavaScript file and try to render it, it might take few milliseconds or even more than that, I had less time than that. I just wanted to look into the file and make a quick decision on the file as it being transferred without being rendered. And the first objective that I have is that I wanted to assume the Pareto principle, which means I'm not trying to cover all kind of obfuscation out there in the context of JavaScript, obviously. I'm looking into the most common, most used JavaScript packer being used in the wild. When I'm saying JavaScript packer, I'm actually meaning the software that will take a JavaScript code and do an obfuscation for that code to get a much obfuscated, much not, a not readable, hard to be debugged kind of code. And in that sense, if I would be able to take 20% of those packers being used in the wild, the most common, most used kind of packers, and I will be able to detect those, I will be able to detect 80% of the samples out there. And that was the objective of my research. So, obviously, if someone is doing a proprietary kind of obfuscation or some highly dedicated, unique tool being used to obfuscate, those kind of scenarios are a bit less, were not in the scope of my research, let's call it like that. And here are some links to that research that I was doing 18 months ago. So I started the research and I had a few questions that I needed to address. That's part of the hypothesis of the research. So why and how JavaScript is being obfuscated? That was the first question that came to mind. What are the numbers behind the usage of JavaScript in the wild? That was also a relevant question, whether my research is really relevant in that sense, in the amount of samples that we can see out there. Is it possible to detect obfuscated JavaScript, right? Can I do that? Can I come up with a solution that will enable me to detect JavaScript obfuscation? And on top of that, and that's a question that I will give you the answer for that, does JavaScript obfuscation mean malicious, right? Does it equal to malicious? And the answer is no. And we'll go into that in detail. But the basic concept is that we see JavaScript obfuscation, and it could be a benign file, it could be a malicious file, and we'll try to figure out why is that and how we can differentiate between those. So with those questions in mind, let's do some sort of an introduction of JavaScript obfuscation. What does it mean? So try to imagine that don't imagine. You can see on screen 3 lines of code for JavaScript, a very basic hello world kind of an example of a function and some writing to console log. And if you take those 3 lines of code and you put it into a JavaScript packer, as I mentioned, the software that will take that code and create an obfuscation on top of that code, you will get a very large file with many lines, unreadable, and very hard to understand. You can see that on screen, but if not, if it's a bit blurry, it's not the issue. The issue is that it's very hard to understand it. But if you will do that same kind of action on the same packer, 1 second after you did the previous obfuscation, you will get another code being obfuscated. The same 3 lines that you were trying to obfuscate, you will try to obfuscate them again, you will get a different result, right? Because when you compare those different obfuscated files after being obfuscated in that sense, the 3 lines of code being obfuscated twice, we can see that they are not the same. Meaning obfuscation creates a challenge in that sense, that if we will come and try to solve the detection issue of those kind of files in the context of trying to create a signature for those files or hash those files, we will have different results because they are constantly changing. And from a defensive point of view, obviously, that's a problem. And that's a problem that I would like to address in some of my research. So we did an introduction. Now let's talk about how JavaScript is being obfuscated. So the most common kind of techniques being used to obfuscate JavaScript file will include having a repetitive kind of patterns and repetitive functioning and variables name into a file. Some meaningless or hard to understand function variables and name as well, right? Trying to create the file that you look into not readable in that sense. Using a variety of techniques to do anti-debugging code. Meaning if someone will try to debug your code, it will be harder for you to do that. And consuming computing resources and time, meaning introducing into the code some dead code, meaning code that will be executed but will not do nothing, just will be executing itself and create a bit more challenges to understand the code and follow the code in that sense, or adding timers to the code, making the code execute much more time. And in that sense, again, in the context of detection, it creates more challenges because it's all about time for you to detect a malicious file. And if that time takes more than a few milliseconds, can take a few seconds, obviously, from a computational point of view, that's a challenge. So this is the how. Let's talk about the why. So the why goes down to the fact that let's talk about JavaScript, right? What's JavaScript all about? So JavaScript is a client-side code, right, running on our browsers in most cases. And once we are saying that a given code is running on our browser, meaning that code is visible to us. It's not a secret. It's not as the example of server-side code that we are not familiar with, or we don't have visibility to that code, and we don't know what that code is executing. We try to guess that. We try to do some sort of a black box thing and try to understand what happens on the server side, but we are not, the code is not visible to us. And that's as opposed to JavaScript, which we have visibility to the code and we can see what the code is doing. Therefore, we can do some sort of debugging for the code. And in that sense, creating obfuscation for that kind of code, it's a security by obscurity. It's our ability to create much more challenging environment to those that try to understand what really happened on the code that we just sent them to be executed on their browser. So that's part of the reason why we're seeing JavaScript being obfuscated, to make the code harder to be read. More to that, make the code harder to be debugged. That's the same objective, right? Create some sort of a code that it will be harder for some of us to understand and debug that. It's not impossible, it's harder. That's the objective. And the second reason for that, on the why, JavaScript being obfuscated, and that I mentioned before, it's a way to create much more challenge for us, the defensive side of things, because trying to hash or use a signature-based text on a given JavaScript file will be harder because JavaScript is constantly changing. And it's very hard to find patterns, and it's very hard to hash those kind of files as a result of that. But there is another explanation that I would like to share in that sense, which is from a defensive point of view. And that's kind of an equation that I have in mind, and hopefully you will see as relevant. So from a defensive point of view, once you need more resources and more time to do your work, the outcome for that would be lower detection rates, right? Because again, if I need to make a decision on a file that's being transferred and I need to render each file, and some of those files contain dead code or timers into those files, and it will take much more time to do the rendering part, then obviously it will take more computational kind of resources for us. And as a result of that, if I will be overwhelmed with those kind of examples or those kind of samples that are being obfuscated, that obviously will limit my detection at one point of time, because we don't live in an environment of unlimited resources. It's always about the resources. And the same equation can be applied to the human resources, right? If we need researchers and analysts to do some sort of debugging or do analysis for a JavaScript file, if we have a lot of those out there, obviously we have limitation in the amount of resource from a human point of view, and that's also a challenging, which is very similar. But there's another approach for that, or another point of view on that from an adversary point of view, because what I mentioned was a defensive point of view, but an adversary point of view means that they will have higher success rate, and that's what they're trying to achieve. They're not trying to evade detection whatsoever. They're trying to make our life harder, and the result of that, have better success rates. As a result of that, get more money out of us. That's the equation that I had in mind. So that's the how and the why. But let's get started with the research itself, right? So when I started doing my research, and I pulled out 4 different samples out there. And those samples, as you can see here, that's a snapshot from some of those samples. And when you look first look into those different snapshots from 4 different files, JavaScript files, being obfuscated, as you can see on screen, led me to the conclusion that these are not the same snapshots. It's not the same code. Well, looks similar, but it's not the same, right? If you will follow the examples here, they're not the same. But it's more than that. I want to tell you, it's not the same, entirely not the same, right? And the reason for that, because these are 4 different files, 4 different threads out there. The upper 2 files are phishing files, right? On the right side, phishing website against some financial service. On the left side, a phishing attack against some sort of an enterprise-associated kind of service. And on the bottom, you can see on the right side a malware dropper that was written in JavaScript. And on the left side, you can see a image card, JavaScript file that was used to try to steal credit cards from a website that file was injected into. Wait, so they are entirely, different in that sense. But I'm telling you that's very similar code, because when you do zoom out from that code, you can see that there is actually pattern that repeats itself in those 4 different snapshots. And the pattern said the following thing: we have an anonymous function here with 2 variables. And inside that function, you can see a variable that contains a function inside of that with a decreasing value. And then we can see that there is a push and shift, meaning there is some sort of functionality that taking JavaScript array and doing some sort of a rotation on that file. Think about it as a payload being constantly changed. And obviously that means that we have something here, right? If we have a pattern, maybe we have the ability to detect that pattern, because that pattern represents that given JavaScript file, or sorry, that given JavaScript packer trying to do some obfuscation for a variety of different files. So that led me to the next phase of my research, saying, hey, so, okay, I can see that code on the left side. Let's try to represent that code in a different way. Let's try to put it into a structural kind of data set. And in that sense, I was using the ability to do that. I was using an abstract syntax tree, AST, which means you take a given file and you create a JSON kind of format for that file, which enable you to go over a given file and look for the relevant things on that file. Meaning, in other words, I don't want to detect the file as is. I don't want to detect the variables name that are constantly changing or the function name. I want to detect some sort of a structure of a functionality that always happens. And in that sense, if we are going to the kind of the abstract kind of structure that we saw before, we can go on the AST file and find different things or different structure-based detection on that file to be able to detect that kind of activity. So in that sense, I created an open source tool. Well, it wasn't open source at the time, and it's still not available, but I'm in the progress of doing that. But at the time, I was creating the proof of concept for that. And that proof of concept was to write some sort of a Python script that will enable me to take a given file, JavaScript file, obviously, represent it as AST, go over that file and try to figure or find the pattern on that file that represent the functionality that I want to detect in that sense. So I had that in mind. Now I had to create those kind of structure-based signatures. And in order to do that, I flagged 5 different packers that were the most interesting and the most used according to the data sets that I have. And you can see it's the 3 first ones, which are, well, relatively trivial in that sense that they are doing a very basic kind of obfuscation, taking a given payload, doing some reshuffling of that payload in order to extract the original code, the JavaScript code that was encrypted by those packers. And here, the 4th and the 5th packer that I was looking into and creating well, structure-based signatures for those packers. And what I wanted you to see here is that the number 4, the packer, the 4th kind of packer that I was looking into, I call it packer with dashes between the letters. And the reason for that is that when you look into the function itself, you can see that the variables of that function are PACKER, right? That's the reason why I call it that. And the 5th one, which is shift push kind of packer, that's the name that I gave it. That packer is the reason that we can see a constant kind of looping and doing some sort of a rotation on the data. And we'll talk about that later as well. So we have now that in mind. We have a tool, a script that will enable me to look into files and make decision, right? I know which packers I want to focus on, which are the 5 packers that we just go over them, right? And I create a signature, structural based signature for those packers. Now it's time to see some results. Now it's time to validate the fact that I was doing that on the wild, on a variety of samples, of data sets of samples. So I was doing that. So on the left side, you can see the name of the 5 packers, and you start to see the data sets that I was using. And the first data set that I was using was a phishing data set with over 100,000 files. The interesting part here is that that data set was really big, but was not as, let's call it, stable as I would like that to be, or not as accurate as I would like it to be. I had a lot of noise in that data set. I had a lot of things that were not classified as phishing from the beginning, but still, I was able to see that 2.1% of the files that were examined were actually matched by this, well, pattern-based signature capability that I created, meaning I have new detection. This is detection that I didn't have before, right? As before, those kind of detection was impossible. Again, as the result of the fact that those JavaScript, obfuscated JavaScript files are creating a much more challenge in a detection point of view because they are constantly changing, right? It's very hard for me to detect it. So that was the first data set in the first step. The second data set that I was using was a malware-associated data set, which was much, much better with 9,000 different samples. And in that case, when we did the examination, we were able to see that 26% of that data set was using JavaScript obfuscation techniques on the data set itself. Which means, in other words, and that's the lesson learned from me here, is the fact that we are seeing a lot of those JavaScript files being obfuscated, well, malicious JavaScript file being obfuscated in the wild means that that technique is widely used. That means that that kind of technique was something that motivates and being used by threat actors to try to create much more elusive kind of files to be detected, right? Security by obscurity, we said that before. That's an interesting point. The third and the fourth data set that I was doing were more into this side of false positive. Me saying, hey, so cool, I have a technique, I know how to detect obfuscated file. I was checking that on malicious data set. It was doing a great job, no false positive, the detection was accurate, meaning I detected those kind of files and they were truly obfuscated. It was not something else for some reason or the other. Now let's try to figure out what happened when I'm looking into a benign data set, such as, for example, Alexa top 18,000 website. Alexa is the ranking kind of website for different highly popular websites out there. So I took the 18 most popular websites out there, I checked them. And the interesting part is that I was able to see that there is some detection on that data set, meaning, in other words, that some of those websites contains an obfuscated JavaScript code. And I looked into that code and those files were accurately, again, good detection in that sense. It's not some sort of detection of pattern that looks very similar to obfuscation. Those were actually detection of obfuscation on those files. And more to that, I validated those websites and I was able to see that those websites are benign. They are not malicious, right? Which is an interesting point. And I was doing the same kind of test now on a random data set with over 60,000 different websites in that sense, and still getting some detection on that side. Meaning, in other words, and that's my conclusion from that data set, is that obfuscation is used more heavily to, well, in the context of malicious files, but that doesn't mean that obfuscation equals to malicious, right? Because we're seeing benign websites that are also doing obfuscation. And here are some of those insights, right, that related to some of the data that we saw before. So I have the ability well, in that sense, I know now that I created a technique that will enable me to detect and obfuscated files, which is great, right? Because I was validating a lot of those detection and I was able to see that there's no false positive. I was able to see that there's over 4,000 new detections that I have, meaning, in other words, that I created a technique that enabled me, in a sense, to have better detection that I didn't have before. We can see that some of those packers are more associated with malicious activity, right? Because we can see that some of those packers only have detections on malicious samples. For example, the AES CTR decrypt, right? You can see hits on phishing data set on malware, but we cannot see any hits on Alexa and random, which means the usage of that packer is much more oriented to malicious activity, statistically wise. And finally, right, as I mentioned, obfuscation doesn't equal to malicious, meaning some of those packers and their core capabilities of obfuscating JavaScript code are being used for malicious activities, but also being used for benign activities. And that led me to the following question, right? The first one is, what is the reason behind the fact that some of those benign websites are using obfuscation? That's an interesting one, and we'll go over that. And the second question is, yes, so obfuscation doesn't equal to malicious. So I have a technique to detect obfuscation, but how can I differentiate between something that is obfuscated and is malicious versus something that is obfuscated and is benign? And I will try to introduce at least a high-level approach or a concept to be able to do that. So let's start with the first question, right? What are the benign use cases for JavaScript obfuscation? So I was going over some of those samples, looking into them. And what I was able to see, for example, the reason why some of those files or some of that JavaScript being obfuscated are for reasons such as email address masking. For example, some website want to put some email addresses on the website as part of the website and want to make sure that, for example, search engines or crawlers or whatever will not crawl the site and do harvesting for those kind of email addresses and then use them for spamming or whatever. So doing a very simple obfuscation for those email addresses will create a bit more challenge for those kind of search engines and scanners because they are not rendering the page, therefore they will have a hard time to extract those email addresses. So that's a very naive but first example. Cookies, client-side cookies functionality. I'm not trying to explain that. That's really bad practicing in the context of security. But some websites are doing that and then doing some obfuscation for those JavaScript files. The most interesting and most prevalent kind of approach was a third-party scripts. Try to imagine that you have some sort of a service that you are consuming or using as part of your website. Let's say translation services, right? It's a third-party kind of service. And you take some code from that third-party and add it to your website. And that third-party service is doing an obfuscation for reasons as, you know, security by obscurity, right? As we mentioned before, trying to create a code that is not readable or hard to be read in that sense. So in that sense, you suddenly have an obfuscated code on your website that you were not aware of. And I was able to see translation services in that sense and advertising services as well. And the last reason that I'm obviously not going to get into, a lot of adult content websites are using obfuscation for one reason or the other. I'm not getting into that, but a lot of mess happens on those websites. And that's one of that mess that's happening there. So we answered the first question on what's the reason we are seeing all of those things out there. Let's try to answer the second question, which is to try to address the issue of how can we differentiate between benign and obfuscated JavaScript, which is benign versus malicious. In order to do that, I'm suggesting a two complementary approach saying the following thing. Let's do the first step, which is false positive. How we can deal with false positive, let's look on the benign side of things and try to figure out what we can do there. And then look into the true positive kind of approach, doing a machine learning classification kind of solution for the problem space we're seeing. Let's start from the beginning. False positives. So think about it like that. So we have two data sets. One is random, the other one is Alexa. And we have for each one of those different websites that contains obfuscated JavaScript. That was part of our detection. Now, what I was doing, I was taking those JavaScript files and I was doing hash for those files. And once I was able to do hashing for those files, I was able to create this kind of map that we see our relationship now, because you're here on the screen, where we are having the blue dots are the actual website themselves, and then the orange are the hash values. So we can start to see that the same hash value is being used by many different websites. And what does that mean? That means that the same source code was obfuscated and then being reused by different websites. And the answer for why it happens, in most cases, it's the third-party kind of scenario that we saw before, right? The same translation service has the same source code, that source code being obfuscated and then being pushed to many different websites out there, right? And as a result of that, we're starting to see those kind of relationships. And when we have those kind of relationships, that can lead us to the point where we would say, hey, so a given hash file is being used, well, which we know it's now as part of our detection, it's obfuscated code. Now we can see that given file is being used on many different domains. Maybe we should say and those domains has high popularity in that sense. So we can easily flag that given hash file as being benign, right? And once we do that, that can eliminate or try to reduce the problem space that we are facing, because we can whitelist in that sense a lot of those websites by our ability to identify obfuscated JavaScript files that we already flagged as benign, because those files are being reused and shared by different domains out there. And only by doing a very minimal kind of experiment, we were able to reduce the problem by 20%, right? If we had much more samples on the benign side of things, random and benign side of things, we would probably have higher percentage, but that's a really good start, and that by itself eliminates 20% of the space of the false positive side that we're able to see. The second approach, as I mentioned, is the true positive approach, which is I was using machine learning kind of exercise to do that. And when we talk about machine learning, we talk about features. So here you can see again the same file that I de-obfuscated over 18 months ago and break it down to small pieces. But when you look into that file, you can actually look at the file and look for the features on that file. So if, for example, if you have an array on the file and that array contains elements, the number of elements on that file can be a feature. The length of the element can be a feature. The type of characters being used on those elements can also be features. So these are features. Again, a different kind of set of feature would be, hey, let's try to count how many identifier we can see on a given file. Identifier would be the variable's name or the function names, or those kind of things on a file. So how many variable names do you see on a given file? That's a feature. Whether some of those variable name or function names start with _0x, which is a notation kind of, or a way to create a variable names that are not readable, which is frequently used by a lot of the obfuscating tools or packers in that sense. That could also be a feature, right? How many start with _0x? A feature, right? With that in mind, now let's try to look on this graph and try to better understand what I was trying to aim to. So you can see on this graph that I took only 2 features, right, out of any given file that I was able to identify as being obfuscated under a very specific packer, which is the push shift packer, right? One of the packers that I was able to create a structural kind of signature for that file, for that packer. So we have 2 features. On the left side, the number of unique identifiers, right? The number of unique variable name and function name. And on the right side, on the bottom, you can see the number of elements in an array that we're able to see on a given file, right? 2 features. Only by looking into those two features and using three data sets, the red and the blue, which are random and Alexa, and the green one representing malware, only by using those three data sets with those two features, we can start to see that there is groups. And in other words, those features enable me to differentiate between different behaviors or different characteristics of files, and being able to say who is benign and who is malicious, because on the most right side and on the upper left side, you can see two groups of files that all of them are malware related, right? And they are really distinct from any other data that we have on this graph. But it's more than that. If we will focus on the center of the graph, where we see a variety of colors over there, even going there, we can see that we actually can do a better differentiation and have better features that describe and be able to differentiate between something that is benign versus something that is malicious, something that is associated with malware data set, right? So having this in mind, thinking about features and our ability to use those features to differentiate and classify different groups or different files by those features, I was using a decision tree to make those kind of decision. And I was using three different features on that decision tree. The first two ones is the one, well, let's start from the beginning. The first one is the number of identifiers, right? Variable name, function name that start with _0x. The second feature was the number of elements in an array that we're able to see in a given file. And the third one is the number of unique identifiers. Again, identifier of variable name and function. So those three features enable me to do better decision making, right? From a statistical point of view. And if we will look on the most right side of this tree, of this decision tree, we will be able to see the following thing. So if the number of identifiers starting with _0x is greater than 20, and the number of elements in array is greater than 17 on a given file, and the number of unique identifiers is greater than 92, only using those three features with those values will enable us to detect 757 of those files as being malicious. And that number is out of the over 1,500 files that were initially identified as being obfuscated by the push shift packer. So in other words, only that side of the tree eliminates 50% of the problem and enable us to detect 50% of the samples that we'll look into as being malicious. So this is decision-making and statistical decision-making in that sense, and how we can use that, right? And again, this is a concept kind of thing that I'm showing you here. It's less about the details and the tuning that might be done or needed to be done on the decision tree, more about the concept that I'm trying to introduce here. So we have a few of those questions in the beginning. Let's try to see if we answered those questions. Why and how JavaScript is being obfuscated? I think we answered that. What are the numbers behind the usage of JavaScript obfuscation? And we're able to see that 26% of the malware associated data set, that by the way, it was not just malware, it was some of that was phishing, some of that was crypto miner, some of that was, mage card kind of attack. It was a variety of samples, but it was really great and very valid kind of data set. We were able to see really great detections on that. We were able to answer the question that JavaScript does not equal to malicious, right? Meaning obfuscation does not equal to malicious, meaning obfuscation can happen also on benign files. We're able to see some examples for that and why it happened. And more to that, we were able to introduce a concept on how to be able to detect and obfuscated malicious JavaScript files, as we saw before. So we have those in mind. Let's start to talk about the next step. Well, the next step for me, obviously. Here are a few of the things that I would like to do next. I would like to release the code for this tool that I was writing. I'm in the process of doing that. I would like to add more signature for additional packers, refine the data set being used. As I mentioned at the presentation, some of the phishing data set was not really that great. I would like to improve that. add more features to using the machine learning kind of approach, and we'll try to explore the ability to create an algorithm that will enable me to detect those kind of, let's call it structure-based signature that I have on Packer files that will enable me doing that much more quickly. Because some of the work that I was doing was manual to try to extract those pattern-based signature from different packages was a manual work that I was doing. So we are toward the end of our presentation. And as you remember, right, the name of the presentation was JavaScript Obfuscation. It's all about the packers with the dashes on the packers, right? And I showed you, said that the reason that one of the packers that I named, it was PACKER, and the reason for that is because, you know, these are the variable names being used on that function. Now, wait, so part of the approach that I was saying, hey, don't use the variable name as a signature, right? They can change easily, right? Don't use, you know, if you have white spaces or someone push some code into a given functionality. Well, try to figure out how we can create a structure to detect some of those things, right? The structure can be the fact that you're using a function and then doing some sort of a loop inside of that function that could be also be structured without naming, you know, variable name, without assuming that there's other parts of code that can be changed on that given source code. So the first one was Packer, right? But as I was moving forward, I was sampling a lot of, you know, more data. I would start to see the different use cases. So I started to see that in some cases, they changed the Packer to packed, right? Which was a good sign that I'm using the right approach, right? My approach of not looking into variable name was a good approach. But then as I move forward, I started to see these kind of odd, you know, underscore, 0x and variable name, right? And we mentioned that before, making the file unreadable, obviously much more unreadable. And that led me to, well, a question that I had to ask myself, well, maybe I should change the name of the presentation, right? Maybe it should be, it's all about the underscore 0x176, right? That might be the name of the presentation because it's constantly changing. So that was my joke for today, hopefully funny. So I think I'm toward the end of the presentation, and I think it's good time for me to have some question if you have any.
Yes, we did receive a couple of questions. The first one is, how resilient is your approach versus Packer developers changing their Packers to bypass your malware detection ML features?
So that's a good question, right? I'm not saying everything is perfect, right? If someone is changing Packer's functionality in that sense and introducing different, you know, approaches for doing obfuscation, that obviously will led me to do some changes in my ability to do some detection. But here's the big but, right? We always try to chase, you know, our own tail in that sense of detection, right? When we try to face adversary improvement, and we try to introduce our own detection as well. So basically what I'm saying is that those kind of changes doesn't happen frequently. And we constantly need to monitor the changes of those packers and adjust to those. But again, since they are not frequently happening, that created, well, if they had to create, if they would have been changed very frequently, that means the adversary are working hard as well, and they're not into that. So that's first answer for that. And the complementary thing here, as the question said, is that moving into a machine learning approach and using those features can eliminate a lot of those changes that might happen on Packer's functionality and enable us to do much better detection. If I be honest, I didn't validate that in the wild, but my assumption is that that approach might close some of those gaps of changes and might lead to a better reaction and changing detection much more quickly.
Great. The second question that we received is, what's the difference between minification and obfuscation?
Sorry, what's the difference between?
Between minification and obfuscation.
Good question. If I understand correctly and remember correctly, minification is more about changing the structure of how the code is being written, while obfuscation try to actually obfuscate. I hope that's the right definition for that. If not, I apologize. But some of my assumption when it comes to obfuscation is that someone is doing a hard job or trying to make and kind of obfuscation that will not be detected easily, meaning someone is trying to evade detection. That's the concept that obfuscation put on the table, and that creates much more challenges because it's not just about changing how the JavaScript file looks like. It's more about someone trying not to be detected and doing a lot of aggressive moves into that. So I would assume that would be the biggest difference between those two approaches.
Thank you. Those were the questions that we received. Is there anything else you would like to add, or if anyone else has any other questions, we have a couple more moments for another question or two.
I think I'm, if there are any other questions, I would love to answer those, or you can reach out to me later on. But basically,
that's right. Or is on Twitter, as he mentioned, so we can follow him there.
Boring persona.
Well, thank you so much, Or, for your presentation today, and thank you to everyone who has attended. It's great to have all of you here, and thank you again for all of your support to OWASP AppSecEU.
Thank you very much. Hopefully next year we'll meet in person.
Yes, that would be awesome.
Yeah. Thank you.
Thank you.